If you've ever struggled to simulate fracture or failure in Abaqus or didn't even know where to begin, this is the only tutorial you'll ever need. We kick things off with a basic tensile fracture test using damage for ductile materials. No code, no subroutine, just the essentials done right. Then we build on that foundation with a spot weld tensile shear failure, followed by shear failure in pinned structures under lateral loading. Next, we ramp things up. A high-speed bullet impact to study how materials respond at extreme strain rates. Then we take things further with a tensile test using the Johnson-Cook damage model, followed by a variation that introduces a welded joint to study fracture behavior. And finally, we scale up to 3D XFEM in a 3-point bending test, capturing crack initiation and growth without predefined path. Every simulation in this Abaqus fracture and failure masterclass is built step by step and visualized live. And if you want the simulation files, just check the descriptions. Let's get started. In this tutorial, we are going to simulate a tensile test using damage for ductile material. So we kick off with creating part. It should be 3D deformable solid extrusion and with the approximate size of 200. We are going to do the same modeling as the previous video, which was the ASTM E8 sub size. So this guy should be 10 and these two should be 30. Now we have to create two lines like this and a line like this. The distance between them should be 6 mm and each of them should be 2 mm away from the side. So yeah, that's cool. And we should create an arc like this and this. And also we are going to have them 12.5. Alright, cool. Now we have to create a construction line which we are going to do the symmetry on. So by left clicking on this one and holding, we can go for mirroring. We want to copy, we pick the mirror line and we choose all instances, and as you see here we have our model mirrored. This one should be 100. So yeah, that's okay. Now we want to use the depth, which is the thickness of the material. For this case is 2, and these lines should be extruded through the material. So we use the define cutting plane, 3 points, this point, and this point. We can create the partition. We're going to do the same thing for this part again, this one. For the convenience, every time I click on the scroll button of the mouse. We have our part created. Now we can go to the property. We are going to create the property for the material. We name it steel. From general, we use the value of density. Here we have the value of the density, and the unit is ton over millimeter cubic. In the mechanical elasticity, elastic 210,000 and Poisson's ratio of 0.33. Now it's time to go for plastic. We have these values. Now here, let me talk about this part. So the first value of the yield stress is actually the yield strength, and the last one is the UTS, which is this part, sigma y0. And if we are going to use the simulation without the ductile damage, the curve would goes like the dash line, but we want to use a failure damage so that we can have a more realistic simulation. So we have to go in the mechanical damage for ductile material and ductile damage. Here we have a couple of fields that should be filled. So this one 0.35, 0.33, 0, and also we have to have the damage evolution, displacement, linear maximum, and 0.4. We click OK. Now we have to create a section, homogeneous, and the material is steel. Now we want to assign the section. I would like to uncheck this one. Okay, now it turns green, and the material is assigned to the part. Now we're good to go for the assembly, create instance and independent mesh. It's better to move the instance to this point, because we are going to create a reference point and it's easier to follow. So from tools we go to the reference point and we use the value of 0, 100, and 10 and minus 0.4. Minus 0.4 is because we are going to opposite direction of the Z. So the reference point is created. Now we can create a set. The set manager create, and let's say RP, and we select this RP reference point and we have the set. Now let's go to the step. The step this time should be dynamic explicit. From the master scaling we use scaling definition below, create, and here we put the value of 1e minus 4 and we uncheck this scale by factor and OK. One important step is here to go to the field output, and from state we use the status because we are going to simulate like the rupture here in the middle of this part. We want to see that, so we click on status in order to see that. And the next thing to do is to go to the history output. We double click on this one. We use set RP, evenly spaced time intervals of 200. We use U2 and RF2. We want to make sure that it's correct, yeah. So this step is done. Now we have to go to the interaction and create a constraint of coupling, choosing the reference point, node region, clicking this part, and OK. Now this part is coupled to the reference point. Now it's time to go to the load. Okay, then we go to the boundary condition manager, create. First we use the symmetry and in cast, to encast the lower bottom part. Move to the left. Now create one from displacement type. We select the RP point. We select all of this and we click OK. Move to the left, but this one, keep in mind, we have to create an amplitude. So we say create an amplitude, tabular, and I can use this one. I can copy here and Control C, Control V. From here we use the amplitude too I created. So dismiss. Now we can go to the mesh. Here from seed part I put this value on 1 mesh, and we have the mesh. Also we want to check the element types. So from here it should be 3D stress, explicit. We uncheck this reduce integration and I think it's okay. Now we're good to go to the job. Here let's say tensile ductile damage. So we click OK, and from the job manager I would submit it. Now the job is completed. We can go to the results. Okay, from the plot contour we can contour the plot, see how the damage happens. Here we can make it slower, or we can go manually like this. And we see here like the fracture happens. Let me switch to this part. Yeah, and the part is torn apart. And the thing about the status I told you about is to see this one. If you haven't checked the status in the field output variable, you are not able to see this one. Okay, so let's go to the ODB history output and choose this two and plot. We have the plot here. From the create XY data, let's go to the operate on XY data, and we can use combine here, U2, RF2, and plot the expressions. So here we see that it is start here linearly, and we had like the damage started from here and it went to the 6 mm of displacement. What we can do right now is to go from here XY data plot and edit, and we select the first one, and by holding shift we can choose all of them and copy. Let's have them on Excel file. Here we can paste it. This one was this placement, this one was the force. So to calculate the stress and strain, first we're going to have strain here and stress. For here we have to divide the displacement by the gauge length, which is 25. Let me show you here. And this one, the gauge length is here 25. So we double click on this one. Now we calculated the strain. Now to calculate the stress, we have to divide the force by the area, so 6 millimeter times 2 millimeter, which is the width, the thickness, and we have the stress here. So as you see, this one, the width is 6 millimeter and the thickness was 2 millimeter. So here we have a stress and strain. We can calculate this, and there we go. Alright, that's it. I hope you enjoyed the video, and if you did, please like this video and subscribe to the channel to see similar videos like this. Today we are diving into a tensile shear spot weld simulation. So as usual, we create the part first. It should be 3D, deformable, solid extrusion, and the approximate size of 300. First we create a rectangle like this. The height should be, the length of the sheet should be 100, and the length should be 30 millimeters, and that's it. This is the part we create done, and the depth should be 1 millimeter. So this is the sheet we have, but we want to create the overlap section and the spot weld as well. So here by partition face, we select this one, we click the scroll button of the mouse, and vertical right, we have to click this one. So we want to create the overlap region here. It should be 30 millimeters, and there should be one spot weld in the middle. Make sure to put this spot here, this tiny spot here, which changes on the circle. Make sure that it should be on one of the main direction, like horizontal or vertical direction. It should be here or here. It cannot be here because it would be bothering us into the meshing section. So I click on this one. It should be 4 millimeter, and the distance to this part should be 15, and it should be 15 to here as well. So we click on the scroll button of the mouse and done. So we have one circle here, which is the spot weld, and one overlap section. But there's a problem here. By using this one, or Control Alt and left click of the mouse, you can rotate this instant. So here we see we have one circle here, but it's not here. So we want to sweep this one and this one through the section. So we left click and hold on this one and use partition cell extrude / sweep edges. We select this one, scroll button, sweep along edge, and we use this edge, and that's it. If you see, here is extruded to the other side. So we want to do the same thing for this line. We click down, sweep along edge, and we click on this edge, and we have this part swept through the edge. So this is the part section. Now we can go to the property. Here, create the property. We say steel. From general, density should be 7.85 E-9. Mechanical elasticity, elastic should be 210,000, 0.33. And for the mechanical plasticity and plastic, we want to select this one, Control C and Control V here. So we have the plastic part, and we can have the damage for ductile materials here, and we can copy and paste these values here to Abaqus. Control C, Control V, and we have this one. And for the sub options in damage evolution, we put the value of 0.44 for the displacement at failure, which explained thoroughly in the previous video, so make sure to check that. So this is the materials properties, and everything is okay. So next we should create a section. Should be section 1, homogeneous solid, and the material is just steel. Now we want to assign the section. The section is assigned here. Okay, now property is done. We can go to the assembly. Here in the assembly, we want to create one instance, and we want to duplicate that. So for our convenience, we put this instance type undependent, and we click OK. Now we translate instance. We click on this one, done. This one should be translated to the center. So this is translated. Now we want to create another part, and we click OK, but we want to rotate this part and put it here. So first we click on rotate instance, and we want to select this one and this edge, and we rotate it 180 degrees. As you see here, it's rotated. If it's okay, we click on OK. Now we want to put it here. So the easiest thing to do is to translate it. We click on this one, scroll button. We put this guy here, and done. As you see here, we translated the instance right over here. So this is the overlapped region, and we have the spot weld in the center, which is pretty great. So assembly section is done. We can go to this step. Here we can create a reference point here in order to see the displacement and force curve, or we can skip that. But here in field output manager, we can first we need to create the step. So let's create the step first. It should be dynamic explicit. Yeah, let's put on dynamic explicit, and here the mass scaling, we click this one, use the scaling definitions below and create. We click on this one, 1e -4, and we uncheck this one, then OK and OK. So let's create the reference point. This one is 0, 0, 0, 0, and this one is so this is 15 here. So let's put the value of 0, 100, and for the Z, let's say -0.5, and we have this one here. So we accept this value, and we create a set here. Create a set. Let's name it RP. Continue, RP, and done. So we have this reference point. We can use that to tie this surface, couple this surface to this reference point in the future, or we can extract the data. So here in the field output manager, we double check on this one. From the state, we should check on status, because we want to simulate this one dynamic in a dynamic explicit mode, and we want to see the rupture. So we click on OK. This is a very important one. So the next thing to do is to go to the history output manager. Here we can say set and RP. What we need to see is RF2 and U2. Okay, dismiss, and this step is done. Unlike the previous videos, I would like to start with mesh this time. So because we selected the dependent part dependent in the assembly, we should mesh it here with the part. So as you see, this one is yellow. It means it cannot be meshed structured. As you see here, we have X. We cannot have a structured mesh, which is the green part. So we want to fix that. To do so, we would like to go to the partition face sketch. We choose this one and this one, and vertical right, we use this one. First, I would like to create a circle here, and then sweep this circle. We select this one and sweep along the edge. I select this edge in order to have the circle in the other part, and from this one partition face sketch part, let's go to shortest path between 2 points. We select this one, we select this point and this point, and create the partition. We have to do that for other parts. Here, here, and this one. So as we extrude all these lines and edges with this sweep feature, we can have green parts here. It means we can mesh them in structured mode. So sweep along edges, this one. We would like to do that for other edges as well. So this one, sweep along this edge. As you see here, it turned green, so we have to do that for this edge again. Here we have this one and this edge again. Now here they are all turned green. It means we can have a very good mesh here, structured one. So we select this part in order to have the lines extruded in that direction. So here we would like to have defined cutting plane. So we select this one, 3 points, and let's use this one, and this one. So we have these lines here, and we should do that for this part as well. So 3 points, this one, it's not selected. Let's rotate it a little. So this point and this point. We create partition here, this one again. So here, this one, and this one. So we have these lines here in this part and the other side. The last thing to do is to create partition in this side, in the inner circle. So we follow the same procedure to create this partition, and we should do that for this one as well. 3 point. I have to do that once more, right? So this one, 3 point. And that's it. We see here we created all parts and surfaces here, and we created some lines, and we can have a structured mesh. So there should not be a problem. Okay, it's time to create the seed edges. Here we should select this edge and the counterpart. So instead of rotating, which is a time-consuming job, we rotate it a little like this, and by clicking on shift, we see we can select different edges. So if I select things like this, and by clicking on control and left click, we can uncheck them. So here I click on shift, I can use this, or even I can have the parts like this here in the wireframe mode. It's easier to select this one. So we carefully select this part, this one, these inner circles. I need to select all of them. So everything is selected. We come back to this mode, and yep. So we want to seed edge, so no bias, and by number it should be 4. Let's see how it goes. So if we mesh yet, the mesh is not bad, or we can put this value on 3. It creates a good mesh here in the center. It's acceptable. We can have finer mesh here, but it's totally fine for this tutorial. So the mesh is over, and we have the spot weld here. So we jump back to the interaction. The reason I didn't want to do the interaction first was that if I wanted to create the interactions and I created the parts, the interaction would be eliminated, and I had to do that again. So here we create the constraint. I name it weld, and I want to tie these 2 circles together. So the bottom of this one to the top side of the other part, it should be attached together in order to simulate the spot weld behavior. So I click on tie, and it can be the surface, but I want to eliminate this surface because I want to select the top surface of the bottom plate. From here, create display group, and on cells I can select these cells to be eliminated. We don't remove them, we just hide them. So we hide these cells, we select them, and we can remove them. Also, I need to select edit selection, remove this one as well. So selecting this one, this one, this one. See here, I accidentally unselect this one. it's totally fine. I'm just wanted to let you know how it's done. So I'm using this surface to be attached to the other plate. So this is the bottom plate and the top plate is disappeared. So by clicking on replace all, we just need to eliminate this tiny part here. So we go to the display group again, we edit the selection, select this one, and this one, and here I click remove. So as you see, this is the bottom plate. By controlling shift I click the bottom plate's surface here, as you see. I hope it makes sense for you. So I click done, and I want to choose the slave surface, which is the bottom part of the top plate. I use surface again, we go to the we select on this one, replace all, and we go to the display group, edit selection. This time I want to select this one by holding shift down and remove. So this is the bottom of the top plate, as you see here. This is the bottom of the top plate, is attached to the top surface of the bottom plate. So here we selected both. If it's hard for you guys, you can select you can deselect the whole bottom part in order to have, you know, accurate and more understandable situation. So the next constraint I want to create is coupling. I use this RP1 and the node region. I select this region here and done. So I want to couple this one to the RP point, which is done. Alright, let's go to the load and interaction. Here from the boundary condition we click on create symmetry. I select the bottom part, which is this one, and I encast. You should move it to left as well. So we encast this part and we want to have the displacement control on the other part. So I create a displacement rotation. I select RP point. First we click on all of them, make them 0, move them to left. Then we want to have 5mm displacement on this part, and as we have the dynamic explicit model, we should create an amplitude. It should be tabular. We can copy this one with Control C here, Control V here. So this should be 0, 0, 0.1 to 0.1 and 1 to 1 and amplitude 1. Okay, as you see here we have a displacement control and the arrow facing toward the Y direction. It means it's going to be pulled down that way. So everything is done, but first, before submitting the job, I forgot something. Here we should put this one on part, assign element types, and this one should be explicit. The element types are explicit, and here let's see, if we don't want to see the deleted element, we can have the element deletion here, but we want to see them. So I would use it as is. And let's go to job. Here we create job spot weld TS, short for the tensile shear. Done. I submit the job, monitor. So it means it will initiate the analysis. And the job is completed. Now it's time to go for the results. Here we see the results. Let's see. So yep, here we have, let's slow down the animation. As you see here, this part is fixed and this part is pulling it. If you see that from this side view, it's more obvious. We can see here it's pulled apart from this zone. Yeah, here's some elements are removed and it torn apart from this part, but as you see here, the spot weld is remained intact, and it just, the elements, the rupture happened from this zone, which is called the HAZ zone. Yep. So this is the final state of this one. If you uncheck the status, you cannot see this element deletion and things like that. So the last thing we can do is to create the XY data, and from the ODB history output you can select these two and plot them. And also you can go from this operate on XY data, you can select combine U2 RF2 and plot the force displacement. And that's it. If you enjoyed the video and the tutorial, please like this video, and if you want to see similar contents, please subscribe to the channel. See you in the next video. If you've ever wondered how to simulate shear in paint connections using Abaqus, you're in the right place. This tutorial walks you through everything: modeling, meshing, contact interactions, and failure setup, so your simulation behaves like it should. And if you want to skip the simulation and get the files directly, watch the pinned comment down below. Let's get started. Create part, we name it plate, 3D deformable solid extrusion 200. I create a rectangle like this. This guy meant to be 30 and this guy must be 100. Also we want to create the hole here. This should be 10, the radius should be 10. Scroll button, the depth must be 10. We have the plate here. Now we want to create lines, partition face sketch. I select this face, done, vertical right, and we should create a line, and this should be 40. Done. And we want to sweep this along the edge, so left click, hold, and partition cell, extrude/sweep. I select this one, scroll button, sweep along edge, select this edge, and create the partition. It's good. Now it's time to create the pen, and everything looks good. This should be 10 again, and 20. Okay, now we have pen and plate. We can go to the property. We name it steel, general density 7.8 E minus 9, mechanical elasticity elastic 210,000, 0.33, and from mechanical plasticity and plastic, and copy paste these values, Control C, Control V. From mechanical ductile damage, we copy and paste these values. So from the sub options, damage evolution, we put the value of 0.4 here, and okay. Now we create the section plate. It's from steel. Uncheck this one in order not to have too many sets, and assign the section. Okay, now it's time to go to assembly, create instances. First create the plate here and translate it, scroll button to 0, 0, 0. Now I create another plate, but this time I want to rotate the instance. Select scroll button, this one and this one, 180, enter. Now it's translated. Click on OK. Now we can translate this one, scroll button, this one must go here. And now it's time to create the pen. Click on OK, translate this pen, scroll button, this guy can go here, and scroll button again. The assembly section is done. Now it's time to go to step, create step. Step 1, dynamic explicit, time 1, Analysium on, and use scaling here. Create scale 1E minus 4, uncheck this one, okay, okay, and from field output manager edit, we should go here. Status should be turned on in order to see the fracture, and the step is done. Now it's time to go to interaction. First I need to create interaction properties, plate dash plate, contact, mechanical tangential behavior, frictionless, and I want to create another interaction property for plate dash pen. Should be mechanical tangential behavior, and we want to have friction with a friction coefficient of 0.1, and normal behavior should be hard contact. So it's time to create the surfaces that we are going to apply the contacts on, and there's one contact between these two plates, and there's one contact between plate 1 and pen, and plate 2 and pen. Okay, so from tools, surface manager, we want to create the surfaces. Create display group, put it on cell, edit selection, select this one, hold shift, select this one and hold shift, select this one, done, and remove them. You select this surface, it can be plate 1 and done, and create the second one, plate 2. We replace everything, and from create display group, edit selection, this one, this one, and this one should be selected, done, remove, rotate, select this one, done. This is the plate 2. We can create another surface inside plate 2, done, and also we should do it once more, this one, remove, inside plate 1, and there should be one which is pen, and replace everything. Display group, this one, done. Replace just this surface, that's true. Inside plate 2, inside plate 1, and plate 2. Okay, let's create the interactions. From here, create, step initial, surface to surface, continue, and from here surfaces, plate 2, we can highlight this one, continue, surface, plate 1, continue. Now this is the plate to plate, and plate to plate, it's better to rename that plate to plate. Now we want to create another one, plate 1 pen, so we select the surface, pen, continue, surface, inside plate 1. It should be plate pen, and we create plate 2 pen, and this should be pen, continue, surface, inside plate 2. Plate pen, continue. Now we have 3 contacts. Okay, we want to create another interaction, so let's first create a reference point here, and here from create constraint we create one rigid body. The point should be this reference point, and the body element should be this one. Okay, now it's done. Click on OK. Now it's time to go to the load boundary condition, create boundary condition 1 initial, this one. We want to rotate and select this one, done. It should be in cast, and we want to create another one here, displacement rotation, RP1, done. Select everything, create another one here, done. Select everything. This one should be 5, and we should create an amplitude 0, 0, 0.1, 0.1, and it goes to 1 to 1. And here we select this amplitude and continue. Okay, the load is done. It's time to go and create the mesh part. So this one cannot be meshed structure, but there's a solution for that. So here, left click and hold partition cell define cutting plane, and here we click on done, 3 points. This should be this one, and this one. Create partition, and we do the same for this one. Scroll button, 3 points, this one, and this one. And we do that for this. Done, 3 points, maybe this one, and this one. Now we can create structured mesh. Now it's time to see the edges. We hold shift and select this one, and hold control and deselect that one. Done. It should be 8. Now we have 8 elements on each quarter of the circle. Also, we want to see the part. It should be 3 mesh. And as you see, this one also cannot be meshed structured, and we should do define cutting plane for this one, 3 points. So this one, and also we should rotate that. Select this one, create partition, doing the same 3 point, this one, and this one, also this one, 3 point, this one, and this one. Now let's do the same. We select these edges and also the one on the bottom. It should be the same, 8, and this one should be 3 as well. Let's mesh it and see that in the assembly, as you see, these lines are in line and also these lines are in line. If you don't see that, it means the meshing is not correct. Okay, now let's jump back to the interaction and see whether the rigid body still exists. So yeah, as you see, because we parted this one, the reference point disappeared, so we can create the reference point here. Okay, now here we want to select the reference point here. Okay, now we want to create another interaction. We name it coupling. We select this one, click on done, and it should be node region. Let's put it on cell, and done. It's okay. Now let's go to the load, and here the load was created on reference point 2, so everything is okay. It's time to go and create the job, pen and plate. Submit, and I come back after the job is completed. Job is completed. Let's go to the results. I put it on this one. We can rotate it a little, and let's see the animation. Yeah, the failure happens here in the shear out formation. If you look at a real-time shear of a pin structure, you see that our simulation is totally in line with this one, so that makes sense. Now let's plot force versus displacement, XY data, ODB field output, and from here check RF1 and U1 from the unique nodal, and here from pick selection from the viewport, we select this one, click on done and plot, and we want to go to operate on XY data, combine U1, RF1, and plot this expression. As you see here, the force goes up and comes down because of the damage load, and here starts failure. And if you look at the paper, you see here follows the same trend. There's a damage load here and there's a failure, and it goes sharply down. But keep in mind that I haven't tried this paper's simulation, and I'm not trying to validate my results with this one. It's just a random paper. That's it. If you enjoyed this video so far, please share your feedback with me in the comments down below. High velocity bullet impact simulations aren't as simple as they seem. There's a hidden secret to making them accurate, and most people get it wrong. But don't worry, you've got me to save the day. In this video, I'll show you exactly how to simulate a bullet passing through a plate the right way using Abaqus. So let's get right to it. Okay, open Abaqus, navigate to the part, create the part. First one is plate, deformable 3D. We want to have shell planner, and let's put this guy on 500. Continue. Let's create the plate here, 100 and 120. Scroll button. Now we have the plate. Let's create the sphere. This should be shell and revolution. Continue. Create something like this. It should be 10. Now with this guy, create lines, we create a line just like this. Then from here, auto trim, we trim this part, scroll button, done, 360, and okay, boom, we have the part. Okay, let's go to the property. Here the material property, general density, this is for steel, 78 E-9 as we have SI millimetric. And let's go to the mechanical properties, elasticity and elastic, 200 E3, 0.3 for the elastic. Let's go to plasticity and plastic. Here I have the material properties here and paste. Okay, now these are the material properties. Now let's create the sections. Sections must be shell homogeneous. One for plate with the thickness of 1, and we create one for the sphere with the thickness of 2. Now let's assign them. This one here, uncheck this one because we don't want to have too many sets. Done. This is a sphere. Okay, now we want to have the plate, this one, and plate. Okay, now the property is over. We can go to the assembly, create instance, select both of them, and the mesh must be independent because I want to mesh it all at once. And okay, now it's time to translate them. This one from here must be translated to here every time I click on scroll button. Okay, now it's time for the sphere. Zoom in a little. This should be center of the sphere. It should go to 100, 50, and 15. Then okay. If we look at it from the side view, we see there's a gap here because we want this sphere to hit this target with a speed. Let's put it back on this one. And the assembly is over. Let's go to the step. The step must be dynamic explicit. Continue. The time period must be 0.00 and 2. We don't need to change anything here. And okay. Now let's go to the field output. Let's go to the state. We go all the way down and we have status here. As we want to see the failure, we need to toggle this on, and this interval should be 100 in order to capture every step. Okay, done, and we are done with this step. Let's go to the interaction. We need to create an interaction property because we want to have a contact between this one, the outer part of the sphere, to this side of the plate. Okay, so from here, create interaction properties, contact. We can have mechanical and normal behavior. It must be hard contact, and allow separation after contact must be toggled on. Now let's go and create the interaction. From step initial, we can have general contact, or even more accurate and better, surface to surface contact. Continue. We select this sphere. Down. Inside this sphere is purple and outside is brown, so we select brown. And surface for the second one, we select this one, and done. It says brown or purple. If I rotate this, you see this side is purple and this side is brown, so I need to select the brown. And this should be finite sliding. Interaction property 1 automatically selected, and done. As you see, these squares, we make sure that the interaction is created. Now let's go to the load. We need to create a predefined field for the sphere, initial, mechanical, and velocity. Select this guy, done, negative 10,000 and negative 85,000. 1000, and V2 must be 0. Okay, the predefined field is created, so we created the spatial velocity. Now let's go to the boundary condition manager and create. We need to fix this plate. So from here, symmetry, continue. So we need to select the sides by holding shift and left click. We can select them, done, and cast because there's no movement on the plate. The load is also done. Now let's go to the mesh. Now we need to sit part. We select this one, done. Let's put it on 4.5 and OK. Then we select the sphere, done, 4.5 as well, and OK. But we need to check the assign mesh control for the sphere. We can put it on quad dominated but medial. Now we click on mesh, select everything, and done, and we have our mesh. But before we leave, we go to assign element type, select everything, done. We uncheck the reduce integration because we have a failure. We want to capture it in the most accurate way, so we need to uncheck this one, and this guy must be dynamic explicit. Okay, meshing is over. Let's go to the job. Here is where we define the shear failure. So we want to create the job. Let's name it shear failure and continue. Okay, we have to write the input file. We need to change something from the input file. So let's go here, shear failure, the IMP file. You can either double click on it, or if you're using Windows 10, you can go open with and select choose from another apps to select the notepad. I go for this one just once, and we need to define something here. By Control F, we can find the material. Let's go down until we find the material properties. Yes, here it is. This is the material properties. We have plastic. We need 1 star. So 1 star shear failure. This is not case sensitive, so you can either write it uppercase or lowercase. Press enter. 0.19. So here we define the shear failure. It means the strains higher than 0.19 would be subjected to failure. Now we need to save it. Done. Let's jump back to Abaqus to create a new job. Let's name it, for instance, crash element. And instead of model, we need to have input file, and here we need to select the shear failure INP. Continue. Okay, now it's time to submit the job. Okay, let's monitor the job. Before the job being completed, if you've enjoyed this video so far, please let me know your thoughts in the comments down below. It's totally free for you, but it gives me the motivation to create more Abaqus tutorials for you. And there we go. Now let's go to the results. As you see, we have the element removal here. Let's see the animation. Yeah, it is so cool. We can also see it from different angles, such as this one, but we can rotate it to see that better. We also can slow it down a little. There we go. Now let's go and see the plastic strain. As you see, after it's done, we have values lower than 0.19, which was the failure criteria. But here, as you see, we have more values. Yep. When it reaches that, it is going to subject to failure. Something else we can do is to plot velocity versus time. So we go to the XY data, ODB field output, continue. Let's put it on unique nodal. Here we have spatial velocity, put it on magnitude, and edit selection. Let's have it on here. We select a point on the sphere and add selection, then plot. As you see, the velocity goes down like in Niagara Falls. With going forward, it means it loses the energy after it hits the target. You can also have the mesh sensitivity analysis in order to have the most accurate one, and with these values, velocity versus time, you would definitely see a convergence after a certain element size. And that's it. If you enjoyed this video, smash the like button and subscribe. In this Abaqus tutorial, you'll discover how to accurately simulate the tensile fracture of a steel specimen with a circular cross-section using powerful Johnson-Cook damage model for the first time. But here's the interesting part. Can this simulation really match a real tensile test? Stick around until the end, where I'll show you exactly how to convert your Abaqus force displacement results into stress-strain curves, so you can compare your simulation directly to a real-world experiment or use that as an input for your Abaqus simulations. Let's jump right to it. Now open Abaqus, create part. As we only have one part, I don't mind renaming it. Deformable solid but revolution. It can be 300. Continue. The part we're going to create is based on the ASTM E8. We have everything required here in this standard. I already created the sketch. You can see that here this should be 15, 20 and 64, 39. Everything we need is here. So let's go create it. Here I need to create lines. So I create two lines just like this. Now this should be 15 and this should be 20. Now we need to create another line somewhere around here. Scroll button. The distance should be 625 here. So let's create the arc here. You need to select this one first, because if you select this one, let's see what happens. The arc is not what we want. So undo, select this one, and we have the arc. Let's add the dimensions of 10. Okay, 10 is good. Now this one can be somewhere around like 25. Now let's create a construction line with this tool. We create a construction line because we want to mirror everything here. Left click and hold and go to the mirror here. And it says, do you want to copy or move? We want to copy. Select the mirror line. Now we select everything here. We don't select this construction line, and done. As you see here, we have the model. Now let's delete this dimension here and set a new value for this one, 64, 39, and we have this value here. Now we need to close this part, because if we don't, let's see, if we want to remove this, it says the section must be closed. So we need to close this one. It also indicated which part is not closed. And done. Because we have two construction lines, it also requires to select the construction line. We select this one and we want to rotate it along this one, 360, and done. Now the part is created successfully. Let's go to the property. From property, we create the material properties here. This is steel, general density, as it is millimetric. This should be 7.8 E-9. Mechanical elasticity and elastic, 210,000. 0.3. From mechanical, we go to plasticity and plastic, but we don't want it to be isotropic. Instead, we want it to be Johnson-Cook. About this one, if we go to this PowerPoint, Johnson-Cook plasticity model, as you see, describe the flow stress of ductile materials, strain rate effects, and temperature sensitivity. According to this formula, this one is the flow stress, and the parameters here are described here. For instance, A is the yield stress, like the one we had before. B is the strain hardening, and N is the strain hardening exponent, while the E.0 is the strain rate as a reference. You can also read about it yourself, but this is the summary of the material properties we have. Then we go to Excel file. I have it ready here. Just need to hit the Control C and Control V here in order to have the yield stress and everything else. Now, from the mechanical damage for ductile materials, instead of ductile damage, we use Johnson-Cook damage. Then we have the parameters here. I need to explain them a little. So according to the Johnson-Cook model, when ductile metals begin to fail, we do have nucleation growth and the coalescence of the voids. According to this formula, we have the strain, and we have other parameters, damage parameters such as D1, D2 to D5, and our fitting parameters according to the experimental. We don't need D5 here because it relates it to the temperature. We don't have the temperature here, so we ignore this one. And we do have the damage accumulation, and this parameter omega indicates the damage parameter, and as we reach the value of 1, the material begins to fail. It's similar to damage for ductile materials where we define the D as a damage criteria, but this one is a little more complicated. So let's jump back to the Excel file to copy everything else here. Control C and Control V. We need to input the damage evolution. We have the displacement of 0.44 and OK. Everything is done here. Then we click OK. Now we need to create a section 1 solid homogeneous, and OK. Then we need to assign this section to this one. As always, we uncheck this one because we don't want to have too many sets. And OK, let's go to the assembly and assemble the model. We need to translate it. So from here, we need to select this one, this tiny point, and we can put it here. Scroll button, and we have it. From tools, reference point, we need to create a reference point just right here. And we're done with the assembly. We can go to step, create a step 1 initial, and it needs to be dynamic explicit. From here we go to the mass scaling, use the scaling definitions below, and create 1e -4, and we uncheck this one. Okay, but it's not over. We need to go to the field output manager and click edit. Here from state we need to check status, otherwise we don't see the failure even if it occurs. So okay, we're done with this step and we can go to the interaction. Now one thing we need to do is to couple this part to this reference point. For that purpose we go to create constraint and coupling, continue, select the reference point, and done. It needs to be a node region. We select this one, done, and click OK. Now as you see, it is coupled to this reference point. Now let's go to the mesh. If we go to the part, we see that it is orangish. It means we cannot mesh it in a structured way, but we need to create some partitioning. I click on this one, point and normal. Let's select this one and this one, and as you see it turns yellow. It means we can have a sweep mesh. Here we need to select this point here, done, point normal, Let's select this one and this line and create partition. As you see, the whole model turned yellow. It means we can mesh it. So if we go to assign mesh control and select everything and done, you see we can have a sweep meshing. We can have it hex. Okay, we can mesh it sweep. That's okay. I would like to put this value on 2 and mesh the model. As you see, the model is meshed. Let's go and check the property. As you see, the material property is intact. Okay, let's go to the loading and boundary condition. Now from boundary condition manager, create, step initial, symmetry, continue. Then let's put this one on cells and we select this part, done, encast, and okay, the bottom part is encast. Now create another one, displacement and rotation, continue, select this one on all, and let's select this RP point. We close it in every direction in the initial, but in the second one, let's put this one on 28, but we need to select an amplitude. So tabular is okay, continue. I already have it on my Excel file. Control C or copy, then we can paste it here. This is the amplitude, but we need to select it, amplitude 1, and okay. Now that's it for the load and boundary condition. We already had the mesh, but we need to go to the part, assign element type, select everything, done. Make sure to uncheck this one. As we're going to have a failure, we need an accurate simulation, so uncheck this one and put the values on dynamic explicit. And let's go to submit the job. So create job 1, JC, Tensile, test, continue. Okay, we can submit the job. Let's monitor it. Everything looks fine. Before the job is completed, I want to ask you a favor. If you enjoyed this video so far, please leave me a comment down below. It's completely free for you, but it motivates me to create more Abaqus videos for you. The job takes a while, but I pause the video here and we'll be back after the job is completed. Okay, now the job is completed. Let's go to see the results. This is the final result, but let's put it back just right here. And from the animation control, we can make it a little slower. Okay, now let's see the animation first. Okay, I'm gonna stop it just right here. And as you see, so there's a fracture here, apparently a ductile fracture. Let's have the force versus displacement. Okay, from here we go to ODB field output, continue, put this on unique nodal, and here RF2 and U2, and from elemental nodes we select the reference point and we plot it. This is the plot, but we need to have displacement versus force. So let's go to XY data once more, operate on XY data, continue, and here select combine, double click on U2, then double click on RF2 and plot the expression. Here, as you see, first we have the linear part, which is the elastic part, perfectly linear. Then we have the yield stress here, and after that we have the damage, and after the damage we have this line. If we don't have the damage criteria, we don't see the drop in the curve, so it's vital to have the damage criteria. If you want to extract the values, you can go to the XY data, temp1, which is the temporary one, click on edit and select the first one, hold shift, the last one, and copy. Then you can go to an Excel file, paste it just right here. So let's say displacement, and this one is force, and you can plot it. We can also convert it to strain and stress. So let's say strain, and here is stress. You need to divide the value of the displacement by the gauge length. The gauge length was 50 according to the standard, and we have this one. This is the strain, and for the stress we need to divide this one by pi, which is 3.14 times d2, which is 12.5 to the power of 2. This is the stress converted. Now we can plot the stress strain curve, which is similar to the force displacement, but the values are different, and you see here the curve is more accurate in terms of seeing the stress and strain. You can also calculate the yield stress and do whatever you want with the data. And that's it. If you enjoyed this video, please like and subscribe to the channel to see more videos like this. Stay tuned. In our previous videos, we explored the tensile behavior of a base metal using Abaqus. Now, in this tutorial, we take it a step further by introducing a weld into the model. How does the presence of a weld affect the stress distribution, deformation, and failure mode? Let's walk through the full simulation process from model setup to post-processing analysis. Are you ready? Let's start. By the way, if you want to skip this tutorial and get the files instantly, just watch the pinned comment down below for the direct link. Let's start with creating part. Create part, 3D deformable solid extrusion, continue. Now we need to create a bunch of lines like this. And from here I want to add a constraint and equal length. These two, select these two, and done. Now I don't need to assign the dimensions for each of them. Now this one should be 10, and if I put this value on 30, you see the other one changes as well. Then we need to create two lines like this and like this. The distance between the two must be 6 millimeters, but we need to select this value at 2. The other one must be 2 as well, so I press escape. Then we need to create arc here. Select this one first, then the other one. It's the same for the other one, and that's it. Now we need to apply the equal length once more on these two. Then here 12.5. Then it's time to create a construction line from here to here. Now we have a line and we want to mirror this side to the other side. So left click and hold on this one and select mirror. First we need to say copy, and we select the mirror line and we select everything, done, and boom, we have our model. Let's put this value here on 100, and that's it. Now done. The depth can be 1, and we have this material here. Now we need to create some modifications. First of all, we need to create the weld. From here, partition face sketch, select this one, done. Then we select this one, and here in the middle we need to create a line like this and a line like this. So create one construction line here in order to make the symmetry. Here let's say 1.5 for this one and 1.5 for this one. Now we have the weld. Let's create that, and that's it. Yeah, the weld is in the middle. Now we need to extrude them through the thickness. So left click and hold on this one and select partition cell sweep. Select this line first, done, and sweep along edge. You select this edge and create the part, and as you see, the part is created. Now we have to do that for the other one. Select this one, done, sweep along edge, and we can select this edge and create. And let's do that for this one first. Done. This one, done, sweep along edge. We can select this one and create. Now it's time for the last one here. Done, select this one, done, sweep along edge, and we select this edge and create partition. Now let's do it for the weld. Select this one, done, this one, and done, sweep along edge. We can select this edge, we can select this edge and create part. This one, then we select the line, done, sweep along edge and this edge, and it is created. Now if we want to rotate the samples, we see we have the weld on the other side, we have other lines, and that's okay. Now let's go to the materials properties. To download the materials properties, let's go to the FEMaster.com. Then from shop, go to the material property packs and select this one, add to cart. Then go to the checkout, fill everything and place the order. It's totally free. Once the order was completed, you can download this one. And I want to open this. Here we have a base metal and a weld metal materials properties. Let's start with the base metal first. So from here we go create material properties. Let's name it the base metal or BM. We need the general density, elasticity and elastic. We need plasticity and plastic. We need also damage for ductile materials here, and that's all, I think. Let's go to this file. We just hit the Control C and Control V here. For the elastic, we go here, copy and paste. For the plastic, we need to select this one and paste. And for the ductile damage, we have this one. Then we need to go to sub option and damage evolution. This should be on displacement, linear, and the value was 0.44. And okay. Then okay, now we have the base metal. It's better to copy the base metal and name it weld. Then we edit this. The density and the elastic modulus are the same and the damage evolution is different, so that's plastic properties. Delete these rows and let's go to the weld metal here and copy this one. Then we go here, simply paste it. Then we need to go to the damage evolution. This one is 42, so we can copy this one and we just paste it here. Then we need to go to the damage evolution and this value is 0.55, and we have the ductile damage, we have the density, plastic and elastic. Then okay, we have a base metal and a weld metal. Let's create the section. So create section here, we can name this BM or base metal solid homogeneous, continue, and we need to select the base metal and okay. Now we need to create another section. We name it weld solid homogeneous, continue, and we select weld. and OK. Now we need to assign the sections. I uncheck this one in order not to create too many sets, and I select this one, then hold shift and select this one, then done. We need to select base metal for them, and OK. And we have this part without the section, so I select it and done. It should be weld and done. If you want to see the differences between the materials properties, or if you want to make sure that it's right, you have to go to here. Instead of property defaults, let's put this on materials. It shows that there are two different materials. If you want, you can change the colors. For instance, you can put red for this, and as you see, this one is red and this one is green, so I would like to put that on property defaults. And we need to go to the assembly. Here we can assemble the model. Part 1, it can be independent as we only have just one part. Translate from here to here and done. Let's reset the view. Then we need to go to the step. We need to create a step. Step 1 initial must be dynamic explicit. Continue. NLGM must be on, and we go straight to the mass scaling. Here we need to use the scaling definitions below and create. Here check this one and put the value of 1e minus 4 and uncheck this one and done. Now this is the scaling and done. Another important thing to do is to go to the field output manager, double click on this one, come here to the state and check the status. If you don't check the status, you won't see the separation or fracture visually. So click on OK, dismiss. Now we're done with this step. Let's go to the interaction. Okay, in the interaction we need to go to the tools and reference point to create a reference point. Let's select this one to create a RP, and from here go to the create constraint and select coupling. Continue. You need to select the reference point first, then done, and we need to select the node region. You select this part and done everything and OK. As you see, this is coupled to the reference point, and now we're done with the interaction. Let's go to the load. Here we need to create the boundary condition. Create first one in the step initial, continue and select this part and done in CAS and OK. As you see, it is applied. Now go to the create. This one we need to create one from displacement and rotation and continue. Select RP point and done. Now check everything because it is the step initial, but we need to modify that into step 1, and the U2 can only displace 15 millimeters. Now we're not done yet. We need to create an amplitude, otherwise there would be a problem and it won't let us complete that. And as you see here, if I click on OK, it's a in explicit analysis we need to create an amplitude. So let's click on this one, check tabular and continue. So you need to create one. This is 0, 0, press enter, 0.1, 0.1, 0.2, 0.2, and we go just like this. You can press enter every time. And 1, 1, and that's the amplitude. Then click on OK. Now you need to select the amplitude, then OK. Now we're done with the load and boundary condition. Let's go to the mesh. Here in the mesh, as we selected the part independent, now we can create mesh easily. So mesh part and select, and as you see, the mesh is created. It can be better, but this is just a simple example and it has an educational purpose. So to further refine that, let's put that on 1, delete mesh, and mesh it once more. Now it's better. Let's go to the job to create the job. But before creating a job, I want to ask you a favor. If you enjoyed this video so far, please drop me a comment down below. It's totally free for you, but it helps me grow and motivates me to create more contents like this. Let's go and create a job. I would like to select and create job manager, so we can name it Tensile test weld and continue. Okay, now that here we can submit the job easily. Let's monitor this, make sure there's no error. Just ignore the warnings, they're fine. And as you see here, it says it is completed successfully, so we have to wait till the job completes. And the job is completed. Now let's go and take a look at the results. This is the result of the final state. Now if we select this one and if we go to the option, viewport and annotation option, let's set all off, just keep the legend and okay. Now here from option and comment, we need to put this on feature edges. It is better. Now for the animation, let's put this on here and let's take a look at the animation. And as you see here is the weld. After the part subject to the tensile test, the weld remained intact. It means the weld parameters were selected in a good way so that it has a better strength and the part is ruptured from non-welded part, which is totally fine. Right now let's go to the XY data, create XY data from ODB field output, continue, and let's put this one on unique nodal. And from here we can have U2 and we can have RF2. Here we need to select the reference point. Here we can select it and plot this. This is the plot. Let's modify that. So once more we go to the create XY data, but this one we would like to operate on XY data and continue. Then we go to the combine. Let's select the U2, then RF2, and we need to plot the expression. Now you have the force versus displacement. It goes up, then elongates for like 5 millimeters, then drops down. A typical force displacement curve. You can also change this one to stress and strain, but you have to do that manually. In the previous videos we explained them completely, but here from here XY data you can right click and edit, and you can select all of the data and you can copy and paste it in an Excel file. So make sure to see the previous video to know how to do that. And that's it. If you enjoyed this video so far, please share your feedback with me in the comments down below. In this tutorial, we're simulating crack growth in a 3-point bending test using XFEM in Abaqus. You'll learn how to model geometry, define material properties with fracture behavior, set up XFEM crack initiation and propagation, and analyze how the crack evolves under bending load. We'll cover everything step by step, from part creation to meshing, boundary conditions, and post-processing with fields like status XFEM, psi LSM, or phi LSM. So let's get started. Okay, let's start with creating the part. Create part. We name it beam 3D deformable solid extrusion and continue. We want to create a simple beam just like this, a rectangle. Then we add the dimensions. The length must be 80 millimeters and this one should be 4, and scroll button, this one, which is the width, must be 8. So we have the beam. Now it's time to create the support or span. I would call that the span. It should be 3D, discrete rigid, solid, extrusion. And continue. Now we create something like this. This should be 8. And this one must be 4. Scroll button once more, and this one should be 8 as well. Now this is the span or support. Then we need to create the crack. The crack must be 3D deformable shell extrusion, and continue. We just want to create a simple line just like this. This should be 1 millimeter. 1 is enough. Okay, same as previous one. The depth should be 8. Now we have all the parts, crack, span, and the beam. Now it's time to go to create the materials properties. We create the material properties, general density, the mass must be 7.8 E-9. Then we go to the mechanical, elasticity and elastic, 210,000 and 0.3. This is for the elastic. Now we should go to mechanical, damage for traction separation loss and max PS damage. Let's put the value of 120 megapascal. Don't mind this if you're not using the 2024 version. And we need to go for damage evolution. Put this one on energy, and the mode should be power low, and 40,000 joules. We copy that and paste it here. Also make sure to put the power on 1 here, and okay, now we need to create the damage stabilization cohesive 1E minus 5, and we have everything: density, elastic, max PS, damage evolution, and damage stabilization cohesive. And okay, now we need to create a section, must be solid, homogeneous, and continue. Okay, and we select this one, then we assign the section to this one, just uncheck this one, and okay, and done. We don't need to create sections or assign materials properties to span or the crack. And okay, let's go to the assembly. We would have an error here if we want to have the span alongside the crack and other things. As you see here, it says a solid rigid part cannot be instanced for the assembly. Now to fix that, we go back to part once more, and we need to go to the span, left click and hold on this one, and go to the create shell from solid. We select this one and done. And as you see now, if I cut this, it is hollow. Before that it was a bulk, but now it is hollow. Now we can create that in the assembly. Another thing that we can do here is also to create a reference point. So I would like to create a reference point right here. So in that case, we don't need to create an interaction of rigid body to call this a rigid body. So this is the discrete rigid and can be used directly. Okay, let's go to the assembly. Now as you see, if I select everything here and click on OK, I can create them. Alright, now it's time to translate them. First this one, scroll button here, can go here, and that's it. Now I need to translate this one, select, and this reference point can go here. Now I need to create more of this. So by here, span, I click and apply. Then I want to do that once more, just like this. Then here, scroll button, reference point, Then you can select this one and put it here, a simple translation, and this one the same thing. Here can go to here. Now we have our assembly. The assembly is done. Now we can go to the step. Now we want to create a step. Step 1, initial, static, general. Then we can go here, 1000, 3 more zeros, should be 1 million. This can be 0.1, 1e minus 9, and 1 as the maximum is okay. Then okay, now we're not done with it yet. Let's go to the field output manager, and here from status you should toggle this one on, status, in order to see the separation. Plus we need to go to the failure and fracture. You go all the way down and phi LSM and psi LSM, check them on, and okay. Now we're done with the step. Let's go to the interaction. We need to create an interaction property. It should be contact, continue, mechanical, tangential behavior, and we would like to have a penalty 0.15, and from mechanical normal behavior we would like to have a hard contact. And okay, now we need to create interactions. From this one, step 1, surface to surface contact, but in this mode we're going to select the surfaces manually. I don't want to do that, so there's an easier option to do, is to go to find contact pairs. If I click on this one and find contact pairs and select them here, you see it shows the contacts, and if I click on OK, and the interactions are created. As you see here, we have one contact between these two, and we have one contact between these two, and there's another one here. So we do have the contacts, and it made our life easier. Now I need to create one another interaction from special, and in the crack, create, select XFEM and continue. We select the crack domain, then we toggle this one on, crack location, and we zoom in here and select the crack and OK. Then OK here. Now we need to create another interaction here in the step initial, XFEM crack growth, and this should be crack 1 and OK. And as you see here, we selected this crack to grow. Okay, this is done. As far as I'm concerned, there's no interaction to be created. Now let's go to the load and boundary conditions. Okay, this is easy. We create the boundary condition from here. I hit create. We can create one from the encast mode. Continue, we select this one, we hold shift and select this one, these two reference points, and done, encast, and OK. Now we need to create another one from the displacement and rotation. Continue, I select this one, and done. Let's check all of them here for the initial step. Now in this step 1 we can modify that, so I'd like to put the value of -8, and OK, it means this span would displace 8 millimeters the opposite of Y direction. And this is the load and boundary condition, and we're good to go to the mesh. Now we need to select part, this one. First we need to assign mesh control. We select this and done. Let's put this one on quad and structured. Okay. Then we need to seed the part. 0.8 is okay. And yes, now this one is meshed. We can go to the beam here. We need to select this one, the same number, 0.8, and okay. Let's create it. Yes. And now if we go to the assembly, you see as we selected the same global seed size, these nodes are attached together. So here is fine. and here are in the same line. We check this one is also in the same line, and here also the lines are in the same one. If you see a mismatch between the two, it means the numbers are not correct and needs to be corrected. Okay, the mesh is also done. Let's go to the job, but before going to the job, I want to ask you a favor. If you enjoyed this video so far, please drop a comment down below. It's totally free for you, but it helps me grow faster and motivates me to create more videos like this for you. Okay, let's create a job. Here we create a job, we can name it 3-point bending XFEM and continue. Okay, then submit the job. It says the following part doesn't have any sections assigned, is okay, and you submit the job. Okay, let's take a look at the results quickly while the job is being run. And yeah, I think that's enough for now. We can terminate the job. From here I click on kill, yes, the job is terminated. It probably be aborted later due to the very coarse mesh we have here or the high displacement, but it's totally fine because this video has the educational purposes. It's up to you to modify it for your model. Alright, let's take a look at the animation. Just like this, as you say, it goes down and the crack grew. Let's stop it here. From option, comment, we can go to the free edges and we can see the crack growth better. And from here, I would like to put it on this one to see that in a slow motion pace. Put it here, then from the side view, and there we go. Here the crack is propagating all the way to the top. Yep. And we can also see other things here like phi LSM or psi LSM. I already explained them in the previous video, what they are and what do they mean. Please check the video. I put the link on top right here. And this is the contour of phi LSM. Let's go to the very end. And we have the contour of psi LSM in here, as you see, and the crack propagates. And that's it. If you enjoyed this video, please smash the like button and subscribe to the channel to see more videos like this. And if you want to learn welding simulation, click on the video on screen before it ends and stay tuned.